So welcome everybody to the first session. My name is Mahmoud Ahmed, and I will be the moderator for this session. I would like to introduce the first keynote speaker, Hiroshi Tsugawa, from the Tokyo University of Agriculture and Technology. Hiroshi is a creator of the MS Dial, a popular universal tool for non-target metabolome analysis. MS Dial is not an R package, but some R packages support its output. Hiroshi will be speaking to us today about his work on decoding mass spectrometry data to understand metabolism in living organisms.
All right. Can you see this screen as a main screen? Okay.
Yes.
All right. Thank you so much, especially for the organizers of this Bioconductor Asia 2021. And yeah, English is my left-hand language. And so that's why, yeah, in future, maybe as non-native speaker, not use English or the science more. Yeah, but today I will use English for my talk. And the title is Decoding mass spectrometry data to understand the metabolisms of living organisms. And before going to my real presentation, let me introduce myself by this slide. I got actually my PhD at the bioengineering department of Osaka University. And as a student, I was a basketball player. And this is me. And I'm still doing basketball with my son recently. And then I started my academic career at RIKEN Research Institute under these two project leaders. Masanori Arita is a computational scientist who is currently a director of DDBJ in National Institute of Genetics. And Makoto Arita is a lipid biologist who is currently the professor of the Keio University. And I was a visiting researcher and visiting scientist of Oliver Flynn lab for 3 years. And actually, I many in and in all the research topics I will talk about today was at home in these laboratories, and I will check those people. Okay, important factors reflects the biological phenotypes very well, and therefore it's very important to eliminate the global metabolome by untargeted analysis for understanding human homeostasis and diseases. Can be applied to many subjects like science, plant science, explore microsoft science, microbiome science. So, however, as many of you know, untargeted metabolomics or lipidomics are so easy because the chemical metabolome is when compared to volume. and to detect this kind of metabolite and this and metabolites data and to annotate, for example, this. So the best practice should be to see the MSMS spectrum of this ion because this mass fragmentation pattern is pretty unique in each of biomolecules. And in this case, this phosphatidylcholine can be annotated based on the existence of phosphatidylcholine specific ion or fatty acid specific fragment ions. However, so this, for example, these many peaks cannot be analyzed manually anymore, and this kind of annotation would be very difficult if the standard compound is not available. So that's why my main research topic is computational mass spectrometry to convert mass spectrometry raw data to metabolite structures for understanding the metabolism of living organisms. For example, so we will see 10,000 ion peaks in a single specimen, and one of my research topic is to develop the automatic data processing method of this mass spectrometry raw data. And also we will see many unknown peaks where the ion cannot be characterized by the reference spectrum. And therefore, my second aim is to create the annotation program for elucidating structures for those unknown spectra. And as Mohamed-san introduced this, so one of my big product as a computational scientist is MS-Dial, and MS-Dial was designed for the data processing of mass spectrometry data, especially for untargeted analysis. And the input of this MS-Dial program is mass spectrometry raw data, and the output is the Metabolome information. And currently, this vendor's format written by red color can be imported directly into this program without any conversion, raw data conversion. And the program supports Metabolomics and Lipidomics recently, and in future it will support proteomics data as well. And this program also supports many kinds of chromatography methods like gas chromatography, mass spectrometry, LCMS, and ion mobility mass spectrometry data. And today I will introduce the Metabolomics pipeline of LCMS and a bit LC ion mobility and SMS technology. And this slide shows the history of MS-Dial program, and it has been launched in 2015. And nowadays, the monthly downloads exceed 5,000. And I'm improving this program by many feedbacks and suggestions from the community. And today, I focus on this research topic about untargeted lipidomics approach using ion mobility tandem mass spectrometry. And if I have a time, and there is a time enough, I will also introduce the topic of plant natural product discovery. And importantly, in this talk, I will focus on the topic of how to annotate metabolites via the mass spectrometry data, which should be a key factor to make metabolomics sufficient for systems biology. And I hope that the audience can recognize the importance of mass spectrometry data science by this talk. And the important things that I would like to say is the MSMS spectrum is the most important information for the annotation of metabolites. And especially in lipidomics, MS-Dial supports comprehensive annotation pipeline using in silico MSMS spectrum libraries of lipids. And this is the example of the MSMS spectrum of this phosphatidylcholine species. And we can find this species-specific fragment ions and fatty acid-specific ions in the MSMS spectrum. And the basic concept of this computationally generated in silico spectrum-based annotation is that MSMS fragmentation pattern will be very similar in each lipid class. That is, so in this phosphatidylcholine lipid case, the mass fragmentation will be started around this ester bond, even if the acyl chain length or double bond number are changed. So that is, we can predict the lipid MSMS spectrum theoretically over G values. It means so without the standard compound information. And we recently created the tandem mass spectra of MSMS spectra of more than 120 lipid classes, which can structurally be characterized by the unique fragment ions. And this black color spectrum is the experimental MSMS spectrum of the displayed lipid structure. And red color spectrum means the theoretically created spectrum, that is in silico spectrum. And we submitted this MSMS spectrum database as lipid tandem mass spectrum atlas 2020, and you can download this MS database from this my website. And this is a kind of complicated slide, I'm sorry, but in addition to making the spectrum libraries, I created the source code to efficiently describe lipid structure information based on the quality of MSMS spectrum. This is the example of MSMS spectrum of sphingomyelin species as acetate adduct form in negative ion mode. And here we can actually see sphingomyelin specific product ion. And although the abundance is very low, we also see the specific ion of acyl chain specific ion like this. And to annotate this MSMS spectrum, we are now using a hybrid scoring system. One is classical spectrum similarity matching using dot product or reverse dot product scores. And actually this kind of similarity matching way is very useful to filter out a noisy spectrum. And we also created this kind of decision tree rule-based algorithms for each lipid subclass. For example, in this case, this program will check the existence of sphingomyelin specific product ion or not. And after this, this program also checks the existence of this sphingomyelin fatty acyl chain specific ion to define the acyl chain composition. And the final description is determined based on the existence of these characteristic ions. And we actually wrote this rule-based algorithms for all of lipid classes incorporated in the databases. In addition, so we performed the machine learning researches to predict retention times and collision cross sections coming from ion mobility data. Anyways, so this kind of retention time from the information of liquid chromatography and the CCS value from the ion mobility instrument should be also used for annotation to efficiently narrow down the candidate of metabolite. And as you can see here, by the test set, the 95% confidence interval becomes around 1 minute for retention time prediction by XGBoost. And the 95% confidence interval for collision cross section CCS becomes around 5 angstrom squares. It should be enough to narrow down the candidate. So if you can trace our, for example, Actually, the liquid chromatography condition is a laboratory dependent, but if you can trace our liquid chromatography condition, you can use the retention time information as well. In addition, the MS-style program now supports the annotation process using the predicted CCS values, which can be used in any laboratories in principle, at least. Yeah, the users will use the, well, the machines incorporating ion mobility instrument. Now, yes, MS-style can narrow down the candidate by using M/G retention time CCS and MS spectral information to determine the unique structure of liquid information. And in addition to just making the retention time and the CCS database, we examined the advantage of ion mobility in untargeted lipidomics. And please see this right panel only. And even though the peaks looks like single in the retention time axis, we can see two distinct peaks in the ion mobility axis. It means, yeah, ion mobility could separate these isomer molecules from in the ion mobility drift tubes, although these cannot be separated in the retention in the liquid chromatography. And also, so when we can use the Burka PASEF technique, which is a kind of data-dependent acquisition in the ion mobility axis, we can determine the molecular species information as well by checking the unique MS spectrum pattern. And we performed the hierarchical clustering analysis, HCA, to visualize the tissue and cell-specific lipid diversity. And this x-axis describes the lipid subclass, and the number of the bracket means the count of annotated molecules in each lipid classes. And this yellow color means simply the lipid subclass was detected, and the blue color means the lipid was not detected in this sample. And in this heat map, we can clearly find the unique lipid subclass considered, for example, bacteria-specific lipid in the mouse species, and many of unique ceramide species were found in the skin, and lipid containing very long chain polyunsaturated fatty acid like 32,5 and 32,6 was found in eye and testes. And this result is a kind of proof of concept to show the performance of our untargeted lipidomics approach in combination with computational technique. And actually, we will update our software program continuously to deepen the understanding of these lipid metabolisms. And furthermore, so by creating unknown MS spectrum, we could annotate several novel lipid subclasses. And one of such new structures was identified by the complete synthesis of this lipid molecule. And this lipid subclass, so an acylated sphingomyelin was unique in kidneys tissue. And this is a extracted ion chromatogram from kidney tissue. And this is the standard compound one, and this is a mixture. And here I show the MS spectrum from kidney sample and standard compounds in negative and positive ion mode. And now we could see the clear consistency between standards and the biological MS spectrum. Then so we clearly said, yeah, this was identified by this structure, and this was really new in this lipid science. And including this, so this is the summary of this paper, and by the update of we classify the tissue subclasses in including novel lipids. And we are now going to the plant products. Right? The reason why we have to create the method to characterize plant natural products, because many metabolites from plants have biologically active sites for mammalian proteins. So nearly half of the commercially available drugs released during this time frame were derived from plant or microorganisms like this. And importantly, around 400,000 plant species have been discovered in this planet, while around 70,000 plants have been investigated for the drug discovery researches. And currently, so 300,000 small compound structures were reported, although it is expected that plant metabolite diversity will exceed 1 million. So therefore, so as described here as a sentence, eliminating the structural diversity of plant metabolite is very important for industrial and this slide explains the difficulty of this natural product and compound or natural product actually takes the spectrum of lipids and protein or peptides, because the molecule consists of the simple building blocks like lipid acid chains or amino acids. But on the other hand, because the structure of natural product is really complicated, the MSMS prediction is not so easy. That's why, so we have to use the reference data from authentic standards. However, so see these panels, even though around 3,000 peaks were detected in the wine LCMS data, only 150 metabolites were characterized by these reference spectrum libraries. And this is because so more than 500,000 metabolite structures have been now recorded in the metabolite structure database, while the number of compounds having MSMS spectrum is less than 40,000. So therefore, we have to make the methodology to expand the knowledge of this MSMS spectrum information to characterize the remaining metabolite information in the LC-MSMS data. And I actually summarized the currently available methodology to characterize the natural product of plants in this review article. And currently, there are many methodologies to annotate metabolite as much as possible. So, for example, which include the molecular networking, which is used as a GNPS environment recently, and it's very popular technique where the metabolite annotation can be performed by the MSMS spectral network. And also there is a methodology using machine learning technique to predict, for example, the MSMS spectrum of only compound structures. Then, for example, we can also utilize the stable isotope labeling methodology, for example, to determine the carbon number or nitrogen number or sulfur number of unknown metabolites by using this kind of experimental technique. And I just want to say here, so the plant metabolite looks like the cosmos, phytochemical cosmos of plant metabolites, and we have to make the computational methodology to eliminate this diversity of plant natural products to efficiently facilitate the drug discovery researches, at least I think. And by this slide, I just introduce one of my work for the structure elucidation research. So first of all, I, for example, created the molecular formula prediction program by the input of this kind of isotopic pattern and MSMS spectrum. And this program, so-called MS Finder program that I created, can predict or can generate the candidate of molecular formulas by the information of precursor ion, electrotype, and mass spectrum tolerance. And then, so this program rank the candidate of molecular formulas by considering mass accuracy, isotopic ratio, and the product to ion information and the neutral losses, something like this. And if the molecular formula information was determined, so next step is to find the candidate of molecular structures. Now this program can look, this program try to search the structure candidates in these Metabolome structure databases and in sometimes PubChem database by using this molecular formula information. And at this example, so we please just imagine now we have 5 structure candidates for this molecular formula. Then next step is we have to rank this molecular structure candidates by using array. Then, so in this research, I created a kind of combinatorial chemistry method where the in silico generated MSMS spectrum is compared to experimental MSMS spectrum information. Then, so please look this right panel, and this axis is a ranking, and just please look only this blue color. And this is a result of the validation of this software program using a total of 3,000 MSMS spectrum data. And it means, so the MSMS spectrum is located as the top candidate by the accuracy of 60% and of 3,000 MSMS data. And within top 3 candidates, this program can put the correct structure by 80% accuracies. And within 10 candidates, so this program can put the correct structures in mostly so 100%. But as you can see here, the accuracy is not enough yet. So that's why as a next research, I used this kind of fully 13C fully labeled plants to determine the carbon number of unknown molecule. The basic idea is, so for example, glucose contains 6 carbon, and the molecular weight is around 180. And if the plant was growth by 13CO2 gas, and the molecular weight of glucose will become 186 by considering the carbon number. And here, by looking at the difference of this M/G value between 12C labeled plant and 13C labeled plant, we can determine the carbon number of unknown molecules. And I created the software program to grasp the difference of this precursor shift by incorporating both 13 C-level plant data and 12 C plant data. And as a result, oh, sorry, this was written by Japanese language, but the carbon, at a total of 3,000 metabolite carbon number was determined in 12 plant species. And by using this carbon information, of course, the accuracy of molecular formula prediction and structure elucidation was improved. And so finally, we could create this kind of figure, and x-axis shows the retention time, and the upper area of y-axis shows the MOBAG value of annotated metabolite in positive ion mode, and the lower area of y-axis shows MOBAG value of characterized metabolite in negative ion mode. And this blue color means characteristic product ions which should be conformed to characterize the metabolite class species. And this red color means neutral losses, which should also be conformed in the MSMS spectrum for metabolite class characterization. And finally, the important thing is that we could annotate more than 1,000 metabolites in a total of 12 plant species. And in addition to already well-known characterized flavonoids, glucosinoids, and phenylpropanoids, our methodology covers various metabolite classes such as steroidal saponins and glycoalkaloids and terpene saponins, beta-carboline alkaloid, etc. And also, sorry, this is one of the summary slides of my talk. And again, at this moment, the annotation of natural product is still difficult. And now many researchers try to develop the annotation program to annotate new metabolite or novel metabolite by elucidating the MSMS spectrum information. And at least for MS dial platform, there are many partner program. For example, so as I show you, so MS Finder is the software to predict the molecular formula and the structure information by looking at the EIMS or MSMS spectrum information. And for example, MS Clean R, written by R languages, can clean up the LC MSMS data by filter out the noisy spectrum. Then the only purified or confident MSMS spectrum information can be sent to MS Finder program or MS Dial program. And also many other software program can support the output of MS Dial program. So that's why I appreciate if the audience of this conference can collaborate with me to facilitate the Metabolomics workflow to efficiently use the Metabolomics data more. Right, this is a summary of my talk, so especially MS Dial environment. So my research topic was the my research topic is to develop the converter, a kind of converter from mass spectrometry raw data to omics data to understand the metabolisms. Then now, so the users of especially metabolomics or lipidomics researcher can utilize MS Dial program in combination with the spectrum library kits and elucidation, structure elucidation tools like MS Finder program and in silico MSMS spectrum like lipids. But I have to continue the development of this kind of workbench so that For example, the emerging mass spectrometry or new fragmentation methodology data can be efficiently utilized in the omics research field. Then, so this is the slide. I appreciate who are the mentor in my RIKEN age, and I appreciate Oliver Finn and Eiichiro Fukusaki, who are my supervisor to learn the metabolomics and the chemoinformatics research. And I appreciate Kazuki Saito and their groups, so to facilitate the discovery or to facilitate the development of natural product discovery. And thank you so much for the audience, and I appreciate your question or comment.
Thank you, Hiroshi. We have just a reminder to everybody, if you want to ask Hiroshi questions, you can ask the questions in the Slack channel, day one, Hiroshi. And we have a couple of questions here. So there is a question here about, is it necessary to consider batch effect or measurement bias when doing machine learning with MS data?
Yes, maybe, yeah, there are several researches of the machine learning to filter out the noisy spectrum. And especially I know the proteomics researchers are doing such kind of researches to predict, to distinguish the really good spectrum from noisy spectrum. And also their group try to predict the intensity or ion abundance of peptide MSMS spectrum, and which was performed now
Okay, another question here from Kozo. He's asking, maybe you mentioned this point at the end of your talk about how the bioconductor community can help with automating the workflow or like linking your software to other existing tools in the bioconductor. So can you elaborate a little bit on that?
Yes, yeah, of course, this MS Layer program can be executed by the Linux and Mac OS or Windows as a command line tool. And so also, so this program itself was written by C# languages. So you can execute this program as a command line tool, and you can develop the platform to, for example, for further statistical analysis or further annotation program from the output of MS Layer program. And in future, so for example, yeah, our group should make the platform of MS Layer program by the Python or our languages, but there is a manpower problem. And so that's why as a community, so I appreciate your effort to create this kind of R or Python solution to facilitate the metabolomics data. But I know, so in R languages, so for example, there is a very famous program XCMS, which can be executed by R languages. And so that's why, well, I don't know if I should create the R solution of MS Layer program in the R environment, but I appreciate your comments.
Okay, thank you. If we don't have any other questions, we will be thanking the speaker, and in a few minutes, we'll be back at 2 p.m. for the next talk. So thank you so much for your contributions, and thanks for the very interesting talk.